And we're back. Okay, hello. Um, and welcome to my live stream. Right. Today's stream will be a bit short, because it's going to be mainly doing optimization. I'm going to show you how to do a basic program optimization, performance optimization in Go, and we will continue where we last left off. I've not changed much in the program. Um, in the last episode, I gotten to the point where we wrote an Ebi10 program, and it would run. But if you watch the last episode, it wouldn't run. When I ran the program, it would not run, and the main reason was because my OpenGL drivers were a bit messed up. You see, I was working on, well, not really, not me. I'm not actually the one who's doing the work, but it's Mark Kramer who's doing some work on Vulkan. He's bringing Vulkan to Gorgonia. Basically, now it means that you can use like max GPUs to run your neural network. And I've been using a modified version of one of those weird graphic driver things. And it couldn't work. So what I did was I uninstalled the program. I uninstalled the drivers. I reinstalled them. And I ran the program. It worked. So to show you that it works, let me see if this is the one. Yes, this is the one. Okay. Anyways, this link on my screen here, it's basically where the repo sits and where the repo is, and you will find that it's not changed much since the last episode. So let me show you that it works. Run this, and you've got hello live stream. You've got a window here, and now you can click, and it goes quite fast. So this is an 80 by 80 tile. As you can see here, it's an 80 by 80. It's just messy, right? So it's an 80 by 80 grid. And this window is an 800 by 800 window. So every cell is 10 pixels wide. Now I'm just going to kill this. And this was actually running on the replicator rule on a torus. I can change this to a plane, for example. And if you run it, you'll see the patterns are a bit different, right? It just goes there and stops. It doesn't move over to the right side. It doesn't spill over. Now, so it works, but it's slow. It doesn't seem slow when it's 80 by 80, but what if we make every single pixel what if we make every single pixel every single cell a pixel? So I make the scale 800 by 800, exactly the same as the window size. Thus, when I run it, you will see that it's quite slow. Oh yeah, I forgot to save it. Sorry. Yep. Run this, and nothing happens. See? Uh, with this, you can actually see the lag. See, I set the maximum TPS ticks per second to 20. Basically, this allows me to basically visualize what's happening. If I comment that out, it will not be much faster. And there is a good I've got some suspicions on why it's not fast. Look, this is really, really slow, right? Because every single cell is now a pixel, but this itself has more pixels, has more cells to compute than the entirety of the 80 by 80 grid. So you can see some very, very weird patterns coming out. It looks almost like a mandala. Yeah, it gets weird and very fractal light, very, very fractal like. So right now what I'm going to do is I am going to do some optimization. So I'm going to close this program, and we are going to do some optimizations. And when you do optimizations, oops, sorry. When you do optimizations, the one thing that you want to do is to profile first. And yeah, if you don't profile, then you're just going in blind and you don't know what you're doing. So in order to profile, you need to write a profile. One of the things you can do is use the built-in pprof profiler that Go provides. So let's do this. So we create a new profile. That's where all the profiles will be written, right? Okay. And then yeah, okay, good. And then we just once you've created a profile, the file to store the profiles. Well, then simply start the profile. So so this basically creates the profile, creates a profile, and then it starts profiling. It starts logging, if you will, all the commands that is being run, and then it will tell you which part of your code is actually hot, and not hot. So this is it, right? Okay, so we can now run this, and then oh right, I forgot to save the file. So okay. Oh right, you can't see this. Oh yeah, right now you can see it. Cool. See, I clicked here, but nothing happened, right? Okay, there you go. And the thing about this is that it's independent on where you click. It doesn't matter. All the computation happens simultaneously from one frame to the next. It is not like a scan line where it scans from the top down to the bottom. Computes at the same time. It just computes everything in one step. Um, if you missed how that works, you can go back to the previous episode. So we're going to let it run for a bit. And then we're going to use the pprof tool to figure out what's making it slow and what we can do to speed it up. I've got some good ideas, which is why you saw me open the other tensor.go thing. I suspect it might be there. I'm not sure. Anyways, let's kill this. We've collected enough of a profile. Let's kill it, and we can do this. Prof.prof. There you go. And so this is the pprof tool. If you're a Go developer, you should be quite proficient with this. It's one of the things that you should be proficient in. And so what you see here is I looked at the top 10 longest executing functions, and what you see here is sync.pool pools get slow and runtime.malloc.gc, as well as all these other things. So this is not quite helpful because it doesn't show me what's really happening, right? So what I can do is I can run web, which opens as SVG file, which we can then open here. Yep, I believe that's the one. Okay, not rendering very well, so let's try using Firefox. Let me pull up Firefox. Okay. So this is the the SVG, and now we can see that the majority of the sync.pool get slow is due to tensor.borrowInts, which is due to the shape.clone, and then you can trace backwards and figure out, there you go, materialize and sum. So we can see that this path, this red path, is taking a long time. And the majority of the reasons why it's taking a long time is because it's doing a materialize, which calls recycle dense, and then it creates a new dense matrix. Matrix, yes. And then it calls like sync.pool, which is slow. And when you allocate, when you create a new matrix, it might allocate new data, underlying data, which will then call runtime.malloc.gc. All right, so that's good. So what was it again? Yes. So tensor.sum, which is called in world.step. Fairly trivial. We know how to fix that. Okay, now let's go back to the coding screen. World dot step. There you go. This is the function that is slow. And the reason why it's slow is because, okay, fine. My eglot's not working. So some would be under API underscore map. Oh, no. So search for map reduce. Okay, so this is the map reduce function, and basically map reduce methods and sum, as you can see here, checks if it's a view, and if it's a view, which is the case if it's a slice. So if your tensor is a slice, then it's considered a view, right? So if it's a view, it will try to materialize it. Basically, by materializing it, I mean creating an entire new so why is it a view, right? Let's go back here. So it's a view because we did a slice here. So let me explain this a bit. So recall that if you've got a grid, a 9 by 9, a 3 by 3, 4 by 4 grid, okay, and then you want to look at, you want to analyze for this one, okay. So you need to slice this bit off and analyze it, okay. And then when you want to analyze for this one, you need to slice for this one. Now, slices in Gorgonia are the same as slices in other multidimensional matrix. So let me show you an example, draw you an example actually, and then I'll show you the example. So if you've got 3 by 3, so this is index 0, 1, 2, 3, 4, 5, 6, 7, 8. Okay, so what happens is it's actually laid out as a flat slice of 9, 0 to 8. Okay, so let's say you want to slice this part. Okay, so what it does is it keeps the same backing array, but the tensor tells the view manager to actually start at item number 4 and go all the way to 8. Now you will note that 4, 5, 6, 7, 8 includes 6, right? If it's going to keep it as contiguous as possible, slicing it as contiguous as possible, but it's going to keep 6 in here. So it needs to skip 6. And the way you do that in Gorgonia is to use something called an iterator. So let me show you a more concrete way of looking at things. Okay, so we just go to CMD and we'll create a new thing called playground. Actually, no, let's not do this. So eglot fails. So okay, so what you see here is I'm creating a tensor and then I'm printing it. It's as simple as that, right? So I need to learn how to save my files anyway. So this is printing out the tensor, okay? And then you can print out the data of what the tensor contains. And maybe you want to print out a type as well. So, oh, yeah, sorry. That's not the type. So type is here. So you can see that the type is a slice of int, and it's basically 0 to 8 in a flat slice, right? So when you slice it, right, I need the utils. Again, this is one of the more annoying bits that of the library. I told you about this, but I'm just going to copy and paste this for now. This is going to be built in the next version of the tensor library. So we can slice 1 to 3. Yep, 1 to 3. So you can see I'm just slicing 4, 5, 7, 8. Right? Okay. If you're following so far. 4, 5, 7, 8. Okay. And now let's look at the data. So that's the raw data. It actually contains 4, 5, 6, 7, 8. So it actually elides this, and the way it does it is through something called strides. So it has a 3-1 stride, meaning for each column it goes, it just skips one. So from this column to this column, it just adds one in the index over here, and then for this to go to this, you need to add 3. So 1, 2, it skips this one and goes here 3. So this is how the underlying data structure of the tensor looks like. And it's pretty much the same as what I had explained over here. Okay, and last thing I can show you is iterator, right? So S will be a dense. S, the type of S is a view, but S itself will be a dense, and so actually I can do this. So we'll print I, and the value. So I and the value would be s.data and the int slice and I. That's correct. So here you see the first index would be 4, then 5, and then the next index would be 3. The next I is 3, and this is how you use iterators to access data internal. Even internally, that's how the tensors access data using iterators. Now, so this is a view. S is a view. It's a slice. It's a slice of the actual T itself. So it's a view on T. And what do we have here earlier? Oh yes. And if it's a view, what it does is it materializes it. So let me show you what I mean by materializing. So let's call it M equals to S dot materialize. Yep. So M, and I'm going to do m.data. I'm going to modify m.data, right? M.data is a slice of int, and I'm going to modify it to 1000. Okay. and now we can also look at this S. So I will explain to you what I mean in this code. What does this code mean? You usually don't have to do this. You usually don't have to do this. You just do this. Right. Yes. Let's format this nicely so that we can see what the hell is going on. So here you see M is 4578. 4578. Then we modified the first element to be 1000, but yet S remains unchanged. Okay. More importantly, T does not the T remains unchanged as well. T remains unchanged. But if I modify S, right, S.data, now if I print this entire thing again, you'll find that S now has changed. But M has not changed at all, right? What used to be 4 in S is now 200. So what materialize means it creates an entirely new tensor. And when you create an entirely new tensor, you need to do a lot of allocations that calls runtime.malloc.gc that which you just saw, and that causes a lot of pain, right? So let's go back here and see how we can fix that. So this is the issue, and we can quite trivially fix this. We can create a new engine to run this specific world engine. Okay, this is the third Superman reference I have in 3 episodes of How Hard Is It. Okay, anyway, we can create a world engine, but a much better way would be to just create a, oh dear, a much better way would be to just create a function, right? We call it func. We call it sum. How about that? And because we only ever use this sum in this specific case, we can write a very, very specific function. Okay. So we create an iterator from it. And then we say that the data is basically a.data. Oops. Okay. And then we can create our 64. Ta-da! That's it. And then we can just replace this entire thing with sum of slice. Sum. And we don't need this. I believe that's the case. Yep. And that's it, right? All right, yeah, so let's see if it runs. Okay, let me show you the desktop as well. And let's see if it's faster. Okay, it's not much faster. But I think I know why. So over here, I'm creating an iterator all the time. Every time I call sum, I'm creating an iterator. But you don't need that. You can just have an iterator. Yeah, you can just create an iterator outside of this function and just pass it in through the sum function. How about we do that? We don't have to look at the profile for now, because I am willing to bet that the profile, anyway, prof.prof. Open a new profile. Ah, okay. I see now why. Okay, I now see why. So this is not really a prof issue. This is a Go mod issue. Yeah, so let me just put a replace statement here. Nope. Let's run this again. Get OBS to see whether this works. Aha. There's a yes. Okay, that's not a difficult thing to do. Ask us. Okay, so with this again, let's see if it's faster. Hey, it's slightly faster, and there's a bit of a latency issue as well. So you can click here and then you move your mouse and then it starts elsewhere. See? That latency issue can be fixed with a TPS, but I will fix it much later. But okay, so this is slightly faster. Still not as fast as I want it to be. And like I said, I suspect it's because we can get rid of this iterator thing and move it out. Making things global variables. Always a good idea. No, not really, no. Okay, so we can change this function to take an iterator. And so we don't create an iterator this time. We create an iterator outside of this function. So you have only one iterator object and it just keeps reusing the iterator object. And thankfully, the iterator object was meant to be used like that because it comes with a reset function method. So let's create an iterator here. Now, if I create the iterator here, it's not going to make much of a difference because it's going to create an iterator in every loop of loop. So what we need to do is we need to move this out of the loop. So for the sake of creating an iterator outside of the loop, we can also do something very tricky, which is to say, we can slice and reslice a slice. Let me explain. So right now we're slicing it here, right? So we do w.buff.slice as a default slice, so to speak, as 0, as 3, 0 to 3. Yes, thank you very much, our watchman. Not interested. Okay, so slice so this is a default slice. This slice object is going to stay outside of the loop. And so now we can do this. w.buff.slice into slice. So slice into is exactly like slice, I believe. So let's go find out. Here. There you go, slice into. I was actually by coincidence working on this, but there you go. So slice into, it's a convenience method. So w.buff is a dense, and you can slice into a given a view, which is this, which we've already allocated outside of this. What does it return? It returns a view slice equals to, and so with this in mind, this slice is going to be exactly the same as this slice, meaning it's only been allocated once and it's going to be reused in all the loops. All right, we need the iterator. So over here we have an iterator. And we can also create an iterator here. I believe that's all we need, right? Hey, it's a lot faster now. So this is a lot faster than the previous two versions combined. That's pretty cool. And let's see, I've been live for 37 minutes. And yeah, this is a pretty quick optimization. Um, yes. So I think okay, what we can do is we can take this loop, we can take the contents of this loop and put it in a Go routine to make it even faster. But to do that, you need to have sorry. To do that, you need to have sorry, my bad. I'm looking at my tablet. It's acting out very weirdly. Okay, so to do that, you need to actually have multiple slices and multiple iterators, as many as there are processors on your computer. And they need to be in a pair. So this is going to be a bit more complicated. How do I do this? I'm gonna have to ignore the errors because I can't be asked to deal with error channels. And because we are doing this on an IJ level, on a row by row basis, we don't actually have to worry about race conditions. Okay, so call this function analyze and analyze. Okay, so what it needs is it needs a slice. Oh no, you can bring the slice along as well. No, you need a slice, yes. Okay, and you need an iterator. Okay, so this is better. So we put this in a tuple. PIT. So we create a new type here, which is a tensor.lens and an iterator. So it's a basic tuple. To make things a lot simpler, we have a tuple. Okay, so this would be t.fst and t.snd. Right. What is wrong with this code? Yeah, ij. It also needs ij. ij. And then this a bit here. Would be t.fst. Yep, you slice into that. And here you just, because I can't be asked to handle, I cannot be asked to handle error channels. I'm just gonna, panic. Generally don't do that. What's wrong with this type struct? False. There you go. And in fact, we can do without this, right? Okay, we can do without this. Because it's going to be returning the same address. Okay. So this would be a function here. This would go like this. This entire thing will now be gone. Just goes go world.analyze, and then we pass in some VIT. You cannot pass in a VIT. You need a channel VIT. Okay, that's simple. You fetch one from the channel. So here we know that we need something called channel of okay, so numproc should be a global variable. Runtime dot CPU. So here is a buffered channel. Right. And then you need a worker thingy. Right. And over here, this will be replaced by a for loop to populate the populate this. Okay. Here you have CH, you have WCH. So this line makes sure that uh it tries to populate um this thing, and it will stop. It will hold if this channel is full. So by the end of it, you need to undo that, and you also need to put T back in pH. Okay. Right. What else does it need? Ah, it needs a work group, a weights group. Oh, it returns here, so we can. Right, now time to populate this. This should run, I hope. Or I could have just made myself ha. Ah, now you need to put weight group here. Okay, let's see this works. Is it much faster? Let's check my H top. Ah, yes, of course. Yeah, it's using all my cores. Very nice. So let's show you what I mean. So when I have this in focus, look at all my cores. Woohoo! It's all going. It's using all the cores correctly. It's doing everything correctly. That's pretty nice. Okay, I think having been streaming for an hour, I think that's enough. I'm actually not feeling that great today. Um, I thought this was going to be a fun thing before I sleep, and it's 9 p.m. now. I think I should go sleep. Yeah, this is looking nice. Okay, and this thing really looks like a weird, like a Buddhist mandala, and just weirds me out. Okay, I should kill it. All right then. Uh, let's look at pprof again. Yep. Right now, if you see right now, what the top commands are the flushing bits. Yeah, the you don't see much of the game of life being done, like the main core, the kernels of the game of life. You don't see much of that here anymore, and that's nice. All right, let me commit this. And that's it. All right, and that's it. Thank you. Um, thank you for showing up. This is the link here again is the repository, which I should probably push now. And yeah, you can follow me on Twitter or start this repo if you want. I've got some good ideas on what I want to do next with this whole game of life thing. Right now, we've only analyzed, we've only done like the replicator rule. There are some things that we can do better. And that's got to do with waiting for inputs in Abiten. The next episode we will deal with that. But for now, I think I'm just going to go sleep. Feeling pretty shit. All right, thank you so much. Follow me on